we apply two forces in opposite directions to a certain object, they can be stretched, like this hair tie, for example. If I pull on it in two opposite directions, it will stretch. Same as this spring. I could hook it to somewhere, so there'll be an upwards force acting against gravity, and then I could put some masses on the bottom of it, which will provide a weight force pulling it down, so the spring will be stretched. It will be extended like this. Now, if, when I release these forces, the object returns to its original shape and size, we say that it has been elastically deformed. However, some objects don't return to their original shape and size when you release the forces. So, like this paperclip, for example, I could apply two forces in opposite directions and stretch it like this, and then when I let go, when I release those forces, it doesn't return to its original shape and size. We say this has been inelastically deformed, or we sometimes refer to this as plastic deformation. So let's talk about the elastic deformation of a spring in a bit more detail. So when we hang that mass off the bottom, we're applying a force downwards to the bottom of the spring, and that will cause the spring to get a bit longer, to extend. We measured that extension from where the bottom of the spring was before I put the mass on to the bottom of the spring after I put the mass on. So from here to here, we're measuring how much longer the spring has got. You've got to be careful when you're measuring that. Now, the force that I've applied, the weight, and the extension, the amount longer that it's got, are related. In fact, they're directly proportional. And the constant of this relationship is called the spring constant. The spring constant just tells me how stretchy or stiff a particular thing is. So force equals spring constant multiplied by extension. And I could plot that graphically. If I took a spring and I added a mass to it and measured the extension, then added a bit more mass to it and measured the extension, and so on and so on. And then I plotted the force, the weight that I've applied, against the extension. For an elastic object, the graph will always look like this. Directly proportional, where the gradient will be the spring constant, because I've got force on the y-axis and I've got extension on the x-axis. Y equals mx, force equals spring constant multiplied by extension. Now, when an object is inelastically deformed, when we have plastic deformation, you don't get a linear relationship like this. The graph will look a little bit weirder. In fact, even for a spring, even for an elastic object, there will be something called the limit of proportionality, and beyond which it stops behaving elastically. If you've ever got a spring and stretched it a little bit and let it go back to its original shape, but then really stretched it hard, you'll realize that you've kind of ruined the spring. It doesn't go back to its original size and shape anymore. We say it has been inelastically deformed, it's been plastically deformed, it's gone past the limit of proportionality, and in that case the graph will start looking a bit like this. While all this is going on as well, just as a little note at the end, when you stretch something, you are storing elastic potential energy inside that object. And we have talked about this before, but just remember that the elastic potential energy equals half times the spring constant times the extension squared. All right, that's it for springs.